So John Mark Foley was going to attend, but Doug's going to do the whole presentation now, and Doug's going to talk about meeting the challenges of formal verification, and he'll take us up. Great.
Okay, great. I'm the only thing that stands between you and your coffee. Okay, I'm going to talk about formal verification today. I'm Doug Fisher. For those of you who don't know me, I'm the Senior Staff Application Engineer in the Reading office, so don't let my Canadian accent fool you. Jean-Marc Faure couldn't be here with us today, so I'm going to do this complete presentation. And by formal verification, what I'm talking to is the formal or mathematical proof of the behavior of your RTL versus some sort of specification, be it by assertions or by C. So the great lead-in from the previous presentation. So next 30 minutes, that's a reminder me to let you know, the original presentation was 45 minutes, but this has been such a popular event. More presentations got brought to bear, and we brought it down in size. But the presentation deck that you have in the handout, there'll be some slides that I don't talk to, but if you have any questions about it, just come see me, okay? So I'm going to talk about the benefits and challenges of formal verification and how you can meet some of those challenges with tools and methodologies and some best practices. So big news for us, last year we acquired SpringSoft, and that brought some complementary technology to the formal technology we had. Gives a more complete solution. Okay, so we have Magellan, which is our property checker, HECTOR, which is our formal consistency checker between C and C and C and RTL and RTL and RTL. And we have Verdi, which is our premium debug GUI that can not only help you debug your assertions, but can also help you write your assertions. And Certitude, which is our mutation analysis tool for helping you measure the completeness of your solution. So some discussions about why people have adopted formal verification. And I know there's a lot of people here with a lot of experience in formal verification. So let's go through this briefly, but this is probably why most of you might use formal verification. The exhaustive verification is a great idea, and particularly for mission-critical applications such as medical or automotive, it's a great thing. But also if you're you have an produce IP and you have a brand to protect, it's very important to have high quality. But even just maintaining the IP reuse from application to application, because everything gets reused these days. So you want to make sure that your verification that you do today isn't the limitation of your IP use tomorrow. Also, sometimes formal is just better at verifying certain things. So it can be very useful for bug hunting. But there are challenges, and some of these were talked to earlier today. And we'll probably talk to later in the day as well. There's problems or challenges with trying to get your adoption of assertions. You are talking about writing in a new language. It's a slightly different concept than writing test bench. Maybe done by different people. It's also can be challenging to realize all the benefits. There's ways of addressing that. There's challenges in making it scale because designs never get smaller. Only the geometries get smaller. The complexity gets bigger. The schedules get smaller. There's also you're probably still going to do some amount of simulation. How do you integrate the simulation with the formal aspects? And finally, how do you know when you're truly done? It's not necessarily clear. So through SpringSoft, we acquired Verdi, which is a premium debug GUI. And I mentioned that you can, most of you are familiar with the idea probably of you could use it to debug assertions. That's great. Most GUIs can. But you can also bring in a dump file, an FSDB file, from an existing simulation, and without having to rerun simulations, develop your assertions. It's a great way to get quick feedback on your assertion design as you're developing them. Now, realizing the benefits. This is sort of the management question. Are you getting bang for your buck? Is it worthwhile? Oh, I don't know. Seems like when you did that formal verification project, you did almost as much work as doing the simulation effort. Well, is it duplication of effort? Was there extra resources involved? Well, there's certainly extra cost. And sometimes formal tools, particularly for people who aren't familiar with formal, the results aren't as satisfying. You have talking to your manager and say, yes, I got all these proofs done except for these 10 proofs. And they're good for the first 100 clock cycles. Well, that should mean something. It probably does in the formal world, but the manager might look at you and say, well, how many cycles does it take for the OS to come up? It's probably more than 100. Okay. And there's also other aspects of, did you have enough properties? Were they effective properties? We recommend that you use formal early in the flow so that the bug hunting efficiencies can come out and be seen. Also, with your formal tools, you should be getting structural assertions that can be, even before you have to write any assertions. Structural assertions can be inferred from the structure of your design. It's a quick way to add value right out of the box. Also, there's checker libraries. These are something that you might get from your vendor, but if not, you can get from Accelerant. Even the assert arbiter, I think, has about 60 assertions that could be added, just like that. And that's for free. You could use assertion IP that comes with your formal tool for some of the more complex protocols, or from your protocol vendor. You could also have specific applications, which I think James referred to. There's a lot of things which you can do which provide high value with relatively little effort. He mentioned SOC connectivity. Connectivity, which is mode dependent, it's a very simple thing to do. Another thing you can do is reachability analysis, coverage reachability analysis. And that's one way of connecting back to your simulation environment. And typically, when people are doing a simulation for regression, you'll get to a point and you'll have a certain amount of coverage. I'm showing here simulation. I'm showing 50%. Typically, it might be 70, 80, 90% before you start asking these questions. But I'm showing 50% here because I want to use the analogy that this is a glass half full, half empty problem. The engineer who's writing the test benches probably thinks that he's half done. The manager or project manager probably thinks, well, he's still got halfway to go. But the real question here is not whether it's half full or half empty. The real question here is, how big is that glass? We talked a little bit about parameterization. It's easy enough to get dead code in designs. It's easy enough to have things that are in your code because they're a manifestation of some sort of debug that you've done. But with the great degree of parameterization, the reuse that's being done today, a lot of designs are being done in a highly parameterizable way that can result in states or coverage that you just can't reach because of the parameterization. How do you find that? Sometimes it will filter out the simulation, sometimes it doesn't. But at the end of the day, the verification engineer will get to a point in the simulation and they'll have to justify how come they're not reaching their coverage goals. Can it be reached? Go through case by case, and then actually find the coverage. So with a tool like Magellan, you can actually do an analysis starting from the simulation coverage that you had, because you know that's reachable. You've already reached it. No point to go back and prove that. And then determine that there is a bunch of reachable coverage for you to still get, but the rest of it is unreachable, and that can be documented for you so that in your verification summary of that you've actually finished, you have proof that those are unreachable states or unreachable coverage. And furthermore, now that you know what is reachable, you can either use one of several methods to actually close on that coverage, including a hybrid formal approach to close on the stimulus to generate that additional coverage. Oh, there's other methods as well, which I'd be happy to talk with you about. Scaling. Formal verification is a complicated business. There's lots of, as your design size increases, the depth, the clock depth of your designs increases, the complexity is a handful. So there are limitations. So you want to make sure you use tools with high capacity and different engines for the right job and being able to orchestrate between these engines. You might also want to consider a hybrid formal architecture of your tool. You're probably going to end up still doing some sort of simulation and formal approaches. You have to consider how you combine the results of both to know that you're done. And you want to make sure that you're using the optimal engines for the job. So this eye chart here is a state space diagram. Each green dot represents a space. If you think about the complexity that a formal tool has to deal with, they're starting from some initial point. Maybe you provide it, and it has to look out from that point and scout out to see where things are. And I liken this to the neighborhood police constable. And just imagine if that police constable was chained to their desk. They couldn't get out and look around. They need to have a look, but they can very well check out the bank across the road. They can check out that nothing's happening next door with the jewelry store. But your house 2 blocks away could be broken into and they wouldn't know. Now, Magellan is a hybrid formal architecture. So it has all the things you'd expect from a formal tool. It has your safety and liveness properties and your automatically extracted properties and assertion IP. But you notice there it also has VCS, which is a simulator. And that's a sign. It's something just a little bit different. In addition to formal, it also has the ability to leave that desk. You can break those chains. VCS is sort of like a car. It can go through the neighborhood. Okay, so it also has a sense of when, the same way the police constable would listen for problems, it can migrate through that state space, checking for issues and problems when the things seem a bit suspicious. In the case of formal, it's because it knows it's trying to prove that assertion fails. So it knows what state has to be close to in order to make that fail. And because you've covered a greater state space, if you have deep errors, deep bugs, you have a greater chance of finding them. But that's, so if we talked a bit about why formal can be better finding some things in simulation, we've talked about why hybrid formal can allow the finding of deeper bugs. But are there some bugs that simulation is not as suitable for? And that fundamentally formal isn't as good for, in a traditional sense. And yes, there is. If you get to complex mathematical data path, your simulation, because of the size of the things that require the combinations and permutations, are going to have a difficult time with that. But formal tools, traditional formal tools and assertions, even assertions, weren't meant to really describe that behavior. That's why I found the previous paper so interesting, talking about doing analysis with C. So we have a tool that compares C to RTL, among other things. So you have a different way of better capturing your specification of behavior and being able to verify it. And that's being used by some leading companies, graphics and CPU companies, to verify the designs. And here's just one example here. Floating point arithmetic unit. 64-bit inputs, 2 of them. 128-bit possibilities. Okay, so in this particular case, they went through opcode by opcode. By opcode 6, they found a problem. Then they were able to verify the solution. But that's one combination of 2 to the 128th. How long would that take to simulate to find that? Okay, so we talked a bit about formal, the different tools you can bring to bear in a problem. Let's look at the problem of completeness. It's a particular issue that with properties, because a lot of the property stuff seems to happen almost under the hood. If you look at properties, it's very easy to get an bigger sense of confidence about what actually is checked. Did you write the right properties? Well, maybe you did. Did you actually put them in the right place? Maybe you did. Did you put enough properties in there to actually do your verification? Maybe. And you're actually generating stimulus, but kind of you are, because you've constrained the tool. Did you put the right constraints on? How have you verified the constraints that you put on your design? In this particular small example, there's 2 blocks, and you could have wonderful properties to verify each of those blocks in isolation. But have you verified the interaction of those blocks? Are they even connected? So now here's another example. The cone of influence might not be what you expect it to be. Here's this idea of a FIFO, FIFO full, FIFO empty, and somehow it's been implemented as this little inverter in here because it's not on at the same time. Well, a formal tool will not have any understanding is that right or wrong. They just know what the property is. So where that would be the expected cone of influence, what's actually being looked at is the reduced cone, because the formal tool is doing what it should be doing and reducing down the size of the problem based on what it knows. And it only knows the design and the assertions that you told. Okay. There are several approaches for completeness. Traditionally, people have looked at assertion density, which is a really crude approximation of, well, do you have codes in that particular block? It doesn't really account for whether the design is complex, it needs more assertions. It doesn't measure whether there were enough assertions or whether the assertions were effective. It just, are they there? Okay. Sequential depth, this is a cone of influence type measurement, sometimes it's called that. And you can actually, here I've described it as a number of clock cycles of path from register to assertion. You're looking for the size of the cone of influence and some way of measuring that complexity. So it does account for complexity, but it really doesn't measure effectiveness. It just means that there's assertions there. And finally, there's mutation analysis that both accounts for complexity and measures the effectiveness of the assertions. I'll talk a bit about that. So I liken, my background is hardware, so when I heard about this, I sort of likened it, thought it was very similar to fault simulation of your DFT type vectors, right? Inserting faults to figure out, does it actually do the job? Because at the end of the day, the expression also came to mind looking at this, the proof of the pudding's in the eating, and only by actually testing it do you actually see that your verification environment was effective. So you add in these faults, these mutations, you run the verification environment. That could be formal or they could be simulation. If the bugs are detected, that's good. If some bugs aren't detected, that's not so good. And in order to have a high quality verification environment, you need to be able to activate the assertions. So you have the conditions by which that bug can come out. You need to be able to propagate to a place where it can be observed. And when it gets there, the detection mechanism has to be effective enough to actually detect the RTL bug is there. All those things are required. Otherwise, it doesn't work. What Certitude does is it inserts the bugs. Some of them will be bigger. Some of the sort of catastrophic bugs, so you'll figure, well, how come that wasn't detected? And also subtler ones as well, trying to get the behavior. And again, finding it is good, not finding it is not so good. So what sort of bugs are we talking about, or mutations are we talking about inserting? They could be stuckets in the same way that HEPD vectors insert stuckets. In some cases, that may prune off, second example, it prunes off an else branch. You change operators. Again, we're looking to run these and find the issues. And the way they're classified, as I mentioned, not activated for NA in yellow, not propagated NP in orange, and not detected in red. Okay, so what we're looking to do is take all those different aspects and measure your verification environment for those. Okay, so here's an actual example to go through. There's the original code, and initially, right off the bat, found some issues where a stuck-at problem on a major signal wasn't being found. Look at the code itself and find out there's non-detects all over it. So we go back, change the code, add some properties. And in the end, what we're left is two redundant bits that we decided to leave in. Okay. Okay. Now, gone all through these results on your formal. What was done in simulation? Wouldn't it be nice to combine those results? And you can. So the same mutation analysis that you can do on your static cases, you can also do in your simulation. Combine the results. In the end, to know that you've activated all the mutations There were the two that you decided to leave in, the redundancies that weren't propagated. And there were no non-detects. So Certitude helps you measure the completeness of your verification environment for formal and for simulation. And it also is a great way as you run it as you're going through and adding your assertions to figure out their degree of effectiveness. Are they adding the benefit that you think they are? So just in summary, the static methods, formal, are an essential part of verification. And they complement simulation and emulation methods. They're a key part of our solution, and we'll always be working on increasing capacity and automation, helping you to raise the level of abstraction, and helping you to ensure your completeness. So you have your Magellan formal tool, which will help you find your properties, but will also help you close on your dynamic simulation. You have HECTOR. If you have floating point problems to solve, it's there for you. You have Verdi as a means of helping you or anybody you're trying to encourage to write assertions, find a nice environment for capturing your assertions in. And finally, are we done yet? For that, you have Certitude.